Hello and welcome to the METHOCEL on Extruded Ceramics webinar presented by IFF and ChemPoint. My name is Jeff Boyd and I'm the Marketing Manager for the Coatings, Inks, and Adhesives portfolio at ChemPoint. And I'll be moderating today's presentation. If you have questions during today's presentation, please feel free to submit them into the live anonymous Q&A. If you do not see the live Q&A function, you should be able to access it by clicking on the icon of the chat bubble with a question mark in the middle at the top right of the Teams window. At the end of the presentation, we'll go over the questions and answer those for you. Presenting today will be myself, Lindsay Torriera, and Roland Bayer. Lindsay is a global communications leader at IFF who's responsible for the branding, marketing, and organizational communications for the company's Pharma Solutions division. Roland is the senior principal scientist responsible for the technical customer application work in IFF's Ceramic Extrusion laboratory in Northern Germany. Start today by covering a brief agenda. We'll start with a quick intro into ChemPoint and IFF. We'll talk about ceramic paste extrusion and types of ceramics. We'll give a brief introduction on METHOCEL, hydroxypropylmethyl cellulose, the general properties and functional properties, IFF's lab capabilities to support customer development, and the METHOCEL product line offering that is relevant for ceramic extrusion. And at the end, we'll leave time for some question and answer. So first, start with ChemPoint. ChemPoint is a full-service marketing and distribution company that was founded in 1999 to be kind of the opposite of a typical distribution model. We've been the authorized distributor for METHOCEL and Polyox in North America and EMEA for 9 years, and we have a dedicated market development team to provide speed and agility of response. And with that, I can hand it off to Lindsay to talk more about IFF.
Super. Thank you so much, Jeff, and thanks for everyone for being here to join the presentation today. We will get to it in a minute, but I wanted to give a quick introduction of IFF since it's likely a new name potentially for some of you. IFF has a really storied legacy, more than 100-year-old company, but about a year ago, we launched the new IFF, which is really a combination and a merger of IFF and the nutrition and biosciences business of DuPont to really create a leading ingredient solution provider across a wide variety of consumer-oriented markets, and with revenues totaling about $12 billion. So our vision and our purpose for the company is really quite simple. It's about applying science and creativity to create a better world, really with a very strong R&D pipeline, deep technical expertise, focus on quality, and a really differentiated portfolio. It's about partnering with customers across those industries to bring them the solutions that they need. The company is divided into 4 different divisions. As you'll see here, Nourish is mostly focused on food and beverage. We have Scent that has really an interesting portfolio in the scent category. Health and Biosciences, really a unique combination from cultures to enzymes to probiotics, and also a Pharma Solutions portfolio that not only touches pharma and adjacent spaces, but also some industrial markets as well, which is what we're here to talk about today. So pleased to introduce Global Specialty Solutions is the business that is serving these industries solely dedicated to industrial markets and customers. We have our own sales and marketing team and partners like ChemPoint, and also a deep technical group that supports solely, again, in the industrial market. A bit about who we are and where we serve. You'll see on this next slide a really diverse portfolio, really broad in the capabilities that we deliver and the functionality that these products deliver. And on the right-hand side, you'll see just how wide-ranging the applications and the industries that we serve in industrial, but really pleased to zero in on ceramics today. And pleased to turn the presentation over to Dr. Roland Bayer, my esteemed colleague, who's going to take you through our technologies for this space. So Roland, take it away. Oh, you might be on mute. There you go.
Yeah, sorry. Thank you very much, Lindsay. So, let me introduce you a little bit into the field of technical ceramic paste extrusion. Let me start with the explanation what we are talking about and what not. So we are talking about the pressing of a stiff plastic and always aqueous mass of ceramic ingredients through a die to form any kind of profile. We are not talking about clay extrusion. Clay is, as you will know, self-lubricating, but it's not used in the extrusion of technical ceramics. Also, we do not talk about thermoplastic extrusion of ceramics. We are just talking about aqueous-based extrusion. After the extrusion step, normally a drying step of the profile is required, followed by firing and sintering of the profile to get the final part. Maybe a little bit post-processing is still required. This depends. And of course, in such a typical recipe, a cellulose ether is always a big contributor for the processing, but also for the final properties. This is not always so well known, but I will give you some more insight. Cellulose ether acts as a viscosifier, as a plasticizer, as lubricant, and as a rheology modifier. And maybe in the past you have been thinking always about optimization of your ceramic raw materials, or maybe also your machinery. This is, of course, something you might be familiar with. But if you optimize also your additive composition, mainly the cellulose ether, you really can get better products, and I'm talking about better end products, higher output, in many cases up to duplicated processing speed, and lower total costs. Lower total costs, for instance, can mean a significantly reduced off-spec rate. And this is, of course, a question of profitability. Next slide, please. There are many types of extruded ceramics in the market, and if you drive a car, you definitely will have seen or you will have used some of them, like diesel particulate filters or fuel catalysts, which are everywhere installed in cars, excepting you are driving an electrical vehicle. Also very well known and a quite big market are Denox filters, which are used in coal power plant purification processes. And not so easily to see for the end user is the filtration of many liquids. Beverages, water, blood, and many other liquids are filtered through ceramic filters. They all are extruded. For the chemical industry, especially for the oil industry and oil processing industry, industrial catalysts are very essential, and many of them are made out of ceramics or are being extruded in ceramic form. And finally, there's one more market which I would like to mention, extruded tubes for many applications. And here in this case, I would like to mention especially silicon carbide and alumina tubes, which are quite often used in high temperature applications. Next slide, please. So this sounds very quick and easily done. You just make a paste and you press it through a die, and just by good luck you get a nice profile. But that's only half of the truth. It's a little bit more difficult, and besides all the enthusiasm, normally you quickly get the experience of some problems. And some of these problems you can solve by the right choice of the additives. I'm talking about, of course, about the METHOCEL additive. Let me give you some example. A major issue in extrusion starts already very early in the process when you make your paste. The plasticity of your paste is significantly contributing to a well done or poor processing. Here in the left corner you can see two pictures. The upper one shows a ceramic paste with very poor plasticity, and the lower one shows the same formulation with a very nice plasticity. Now you will believe, it's just a question of time, how long you need, and as longer as better. In many cases you are right, but I have seen cases where even after kneading of several hours, you still have these little dumplings like in the upper picture on the left. So the plasticity did not increase, but with the right choice of cellulose ether, it is easily done. And you get a mass like it can be seen on the picture below. A second problem, typical problem, is the so-called shape retention. Shape retention of your profile especially has a high importance when you extrude hollow profiles like honeycombs. Here in the upper picture, you can see a picture of shape retention problem. In this case, it was extrusion of silicon carbide to a hollow profile, of course, in honeycomb. As you can see in the upper part of the picture, some segments collapsed a little bit. At least they are distorted and sagged, and this is off spec. You cannot sell away to a customer. Silicon carbide is expensive. This reduces your production speed and leads to off spec, which is costly. What you like to get is a stable rectilinear structure, as you can see in the picture below. And cellulose ether definitely contributes to the solution of such issues. Now we are coming to a major issue, crack formation. I'm quite sure there's nobody here in the line who never saw crack formation during extrusion. It can happen at many places, and it can have many reasons. In some cases, the right choice of METHOCEL can really help and can heal a problem or can solve a problem, even if the METHOCEL is not the reason of it. So, for instance, typical reasons for crack formation are wrong batch processing, wrong mixing, uneven distribution of water in the batch. Has to do with so simple things like cutting the profile after the extrusion step, with handling the profile into the drying room, with the drying room conditions, with the air distribution in the drying rooms, with calcination conditions, and so on and so on. There are many, many contributing parts, but cellulose ether, in some cases at least, is able to solve some issues which you cannot solve with any other tools. Next slide, please. Now let me come to the functional properties and benefits of METHOCEL in the extruded ceramics. So as I said already, main visible effect is of course a viscosity build up in the paste, and not so obvious but extremely important is the water binding force. I said already METHOCEL is a binder, but it is also a binder for the water. It keeps the water in the paste even under high pressure. Sounds unimportant, but it is of a very high importance. If you ever have seen a water drop falling out of your machine, for instance, at a seal or some other parts, this can lead to extremely fast development of pressure and to a high danger for the machinery. Machineries, even with 1 centimeter thick steel, can break. And this is a question of the water retention capability of the cellulose ether, and definitely this is here's a contributor in such a problem. If you have ever seen such a problem, please immediately replace this cellulose ether or reformulate it. It binds the ceramic particles, it lubricates the paste and plasticizes it, it acts as a rheology modifier, as I said already. There are many different possible rheologies you can choose. from Newtonian to pseudoplastic. And there are many other details we can discuss offline if you like. And of course, I want also to address the topic of shape retention and paste ductility. Both are impacted heavily by the substitution of the cellulose chain, which means, translated into, let's say, normal words, it is depending on the so-called chemistry of the METHOCEL. So there are grades where the paste ductility is high, and there are grades where the paste ductility normally is lower. Then the stiffness is higher. It has advantages and disadvantages. So it is always a question to find the optimum for your recipe and what your individual conditions really require. Next slide, please. Our METHOCEL is derived from nature. Our main raw material is wood, cellulose from wood or cotton. And after a very complex processing in a high pressure reactor, at the end we get white powder, which is water soluble and binds and lubricates the ceramic paste. Chemically seen, it is a HPMC, hydroxypropyl methyl or MC, which is a methyl cellulose. These are two different classes, and in order to characterize them a little bit easier, these classes received letters. So we have a METHOCEL A class, this is a pure methyl cellulose, and several HPMC classes, METHOCEL E, F, K, and J. At the end of the, please go back. Yeah, thank you. At the end of the slide, you can see a segment of a cellulose chain, and you will easily see there are repeating units, so-called glucose units, and every repeating glucose unit has 3 free hydroxyl groups. And this is where we make our reaction process, where the reactions take place, where the methylation and the hydroxypropylation takes place. And we can steer the amount of methylation degree and the amount of hydroxypropylation degree, and this characterizes the differences in properties, mainly the differences in properties of our cellulose ether. So for instance, the hydrophobicity, hydrophilicity, can be steered and influenced by this choice of parameters. Next slide. Yes, if you look now, if you make a graph presenting the methoxylation content and the hydroxypropylation content, on the 2 axes, you will get some boxes, and these boxes represent the specification windows of our cellulose ethers. And you can see very below there is also the A class, but it is just a line, it's not a box. And the reason, I said already, METHOCEL A is a pure methyl cellulose, and of course hydroxypropylation content is 0. That's the reason why it is just a line. Next slide. Yeah, in order to support you in your development work, but also in order to produce lots of data, to get experiences with ceramic formulations, and in order to develop better products, we have established a ceramic extrusion laboratory already 25 years ago. Some pictures from our lab are shown here on the first slide. Left above, a fluidized bed mixer, which we are using for the dry mix. This is the only way to get a homogeneous dry mix between heavy powders, heavy particles like silicon carbide, or even, there are many others, zirconia, for instance, and light particles for instance, cellulose ether. Yeah, if you have a slowly running mixer, you never will get a homogeneous distribution, and this is, by the way, one of the reasons for a later crack formation. Later on, after you have received a homogeneous dry mix, you spray water in, and the process is ended when you get small dumplings, very small dumplings, which you empty out of this container and fill into a paste kneader, which you can see left below. This is a typical kneader, which further plasticizes the mass before you put them into the extruder. Our water dosing unit you can see right above. This is a simple equipment, but very useful and precise. What I showed you is a two-step process. Looks a little bit old-fashioned, but it leads to very nice results. There are also ways to do it in one step. For that, you have to look to the picture right above, right below. This is a high shear mixer, a so-called Irish mixer, which is a totally different technology. It works in one step, and I think in most cases you can get very similar results. Next slide. Okay, now we have received the paste, and what now doing with the paste? The first is not to make an extrusion test, but first to test the properties of this material. For that, please have a look to the two pictures left above. In the first line, we are using a torque rheometer from Brabender, which is nothing else than a small kneading chamber with two kneading pedals, which you can see in the middle picture. But they have, in this kneading chamber, there is a torque sensor. And this torque sensor indicates very precisely where the gelation starts, because at the point of gelation of the cellulose ether in the ceramic paste, your torque will rise up. In an extrusion test, your pressure would rise up. The next picture shows our capillary rheometer, which is which we misuse as a piston extruder. And then in the lower line, you can see our single screw extruder. This is an 8 centimeter machine, and a double screw extruder, which we are using as well. Next slide. So now we are coming to a very big and important topic, which leads to a serious understanding of every individual paste you are formulating. I mentioned already that a limit of all extrusions is the gelation of the cellulose ether. This is a very unusual property. Normally, if you heat up a solution of any ingredient, let's say sugar or salt, the solubility increases with the temperature. But here in the case of cellulose ether, it's exactly in the opposite direction. At a certain temperature, the solubility is decreased and the cellulose ether starts to flocculate out of your solution. And if this happens in a ceramic paste, you can't see it anymore because of the invisibility of the ceramic particles, but it happens. And this is a high danger for your extrusion process. And that's the reason why we have made a lot of work on this topic to enable you a safe extrusion. Especially for your plant, it is of importance because you do not have such a nice temperature control in your plant like in the lab, at least in most cases. Yeah. We defined a so-called temperature window of safe extrusion, where you can safely run your extrusion process also under plant conditions. And we defined this safe window to be 10 degrees below the gelation temperature. Where the gelation temperature is, you can measure with this torque rheometer trial. Here in this case, this is just an example. In this case, the relation temperature is in the range of 50 centigrade, and this means the safe window of operation ends at 40 degrees. Now, your question is, this is 40 degrees. Yeah, maybe this is not a large space. Yeah, you might be right. Then please enlarge the space. There are different possibilities. We have a toolbox. Yeah, it's like in a car repair. And by modifying the conditions, you can move this relation temperature upwards or downwards, depending on your needs. So the safe window of extrusion has a lower end, which is of course defined by your water cooling conditions. Please do not think about your lab. In the lab, normally you have a very nice control. Please think about your plant conditions. This is really the challenge. In the plant, you might run your extrusion day and night, 24 hours per day. You might run in winter, and in summer you might face a challenge that the tap water changes the temperature between the seasons, and you might face many other challenges. One of them is the extruder in the lab normally is smaller than in the plant. If the extruder is large in the plant, of course the cooling conditions are worse compared to the lab, because the ratio between a cooling surface and processed material is very different from the lab, and normally it is a negative effect, which leads to an increase of temperature in the processed phase. This means you are coming closer to the relation temperature compared to a similar trial in the lab. So I said the lower end is defined by your water cooling conditions. The upper end, however, is defined by the relation temperature of the cellulose ether in your paste. There are 5 reasons to influence this relation temperature, or 5 origins which contribute to the relation temperature, and they are very individual, depending on 4 recipe parameters and 1 processing parameter. And this is just an example. Next slide. This is another very nice example demonstrating how important it is to stay in a large distance in this safe window of operation. So in a certain test, in a test batch, we measured with our torque rheometer that the relation temperature of the cellulose ether in a certain mix was 58.6 centigrade. Then we made 4 extrusion tests at 4 different temperatures and checked the profile quality. Please have a look to the first picture. We extruded this material at 50 centigrade, so nearly 10 degrees below the relation temperature. The profile looks very well, no holes, a very smooth surface, everything is okay. But then 5 degrees later, 5 degrees higher, a second picture, you can see the surface shows already a slightly cloudiness. The profile is still even and looks still okay, but you will realize that first micro defects occur, but maybe you can still sell this material. You should make a test after sintering. Then picture number 3, very significant. You are still 1 degree below the relation temperature, but you get already a very coarse and porous structure, deformation of the shape. It was a full profile, not a hollow profile. A hollow profile would look even worse, you can be sure. And smaller pores on the surface. Finally, the extrusion test at 60 degree, more than 1 degree above the relation temperature. This is a disaster. You never would sell this. Definitely this all is off spec, already extrusion here in picture 3 is all defect, definitely. Yes, this is just for demonstration purposes to show how important it is to stay away from this gelation temperature. Next slide. Some more examples here to show you the relevance, how to formulate the relevance of different parameters. In this example, we would like to demonstrate the relevance of the concentration of the cellulose ether. Here in this example, we are using 3 METHOCEL concentrations. In all cases, we were using METHOCEL F for M. First test run with 2% in the mix. Please have a look to the dark green line. First, the line shows a slight decrease. This is a normal effect which you observe in every polymer solution when you heat up polymer solution. Normally the viscosity drops. But here in this case, you are coming to the gelation temperature close to 60 degrees, and then there is a sharp rise of the extrusion pressure. And why? Because, of course, the cellulose ether flocculates. It's not soluble anymore. If it is not soluble anymore, it cannot contribute to plastification, lubrication, and so on. And that's the reason why the pressure is rising. Second case with 3.5% of F4M. Now we are coming to the second line, starting at 26 bars extrusion pressure. You can see that the extrusion pressure drops significantly, so the lubrication is definitely better. This looks very good. This is an advantage, but at the same time you get a disadvantage because the gelation temperature drops from roughly 60 down to roughly 45 centigrades. This means your window of safe operation is reduced by 15 centigrades. This is a lot. If you have difficulties in cooling, this might be hard. And example number 3 with 5% of F4M, you can get still a little drop in the extrusion pressure, but this is not significant anymore. However, you get also a further drop in the gelation temperature. And now your window of safe operation is really getting extremely narrow, so that nobody reasonable would recommend such a recipe. Yeah, there might be reasons to run with a high content of plasticizer for very complex profiles, but then you are forced to extrude very slowly. But we should discuss those topics. There might be reasons, there might be options to save money, to reduce the concentration of additives with other solutions. Next slide. Yes, 3 other examples now. We are comparing 3 times same concentration of 3 different cellulose ethers. Here in this graph, we are talking not in percent, but in pph. Sorry, but maybe you are doing the same. pph means parts per 100 weight, and this is a slightly different calculation. So we are calculating parts of cellulose ethers on top of 100 parts of ceramic dry ingredients, and of course then you have still to add the water. Here we are comparing 3 very different behaving cellulose ethers. Let's start with a dark red curve, which shows first a long, very linear drop in pressure, because I said already, if you heat up a polymer solution, the viscosity must drop. But at the end of the scale, somewhere at 80 or 85 centigrade, the extrusion pressure drop stops and there is a rise in temperature. And this is due to the flocculation of the cellulose ether. But this METHOCEL K chemistry is very well known to lead to very, very high gelation temperatures. So the safe window of operation here is somewhere up to 70 degrees, which is probably good enough for nearly all cases. METHOCEL F for M is a second example, the other red curve, which shows significantly lower extrusion pressure and also a lower gelation temperature, somewhere in the range of 60 degrees. And for special cases, we can recommend also the A chemistry, the pure metacelluloses. However, they have a combination of all disadvantages you have seen so far. They show high extrusion pressure and a very small window of safe operation, because the gelation temperature here in this case is already at 45 centigrades. However, there are reasons to use it, and it is used in the market. For instance, the METHOCEL A grades give a wonderful shape retention in complex profiles. This is a positive, this is a benefit we should mention. Next slide, please. Yeah, I would give, at the end, I would like to give some typical formulations for ceramic extrusions. You might know it if you run extrusions every day, but if you start just with this topic, you might be happy to see some guidance. Normally you start with 100 parts of ceramic ingredients, whether it is colloid, silicon carbide, titanium, alumina, whatever. There are many options, and 1 to 8 parts of METHOCEL. And depending on the ceramic raw material, for instance, alumina, you choose a lower content of METHOCEL, but if you choose, for instance, silicon carbide, you need a higher content, 4 to 8 parts per weight. In alumina, just 1 to 3. An additional lubricant is Polyox, which is used nearly in all cases if you extrude alkaline titanium honeycombs for Denox filters, but it is used also in other extrusion applications, and it is an additional lubricant leading to a wonderful plastification of the mess, and it has not a big effect on the gelation temperature. Further lubricants are used more or less everywhere. You can read a lot of literature about the further lubricants and plasticizers. Please use them only as much as needed, because a higher amount always leads to problems in the cohesion of the ceramic particles, and also they contribute to a reduced gelation temperature. So it's always a compromise, as much as needed, but not more. And if you extrude filters, then it might be worth to think about pore formers. There are many pore formers in the market. And of course, at the end, you need a certain amount of water to get a stiffy paste. And the amount depends, of course, on several parameters like the particle size distribution, like the surface of the ceramic particles, and some other parameters. Next slide. Our product line. Yes, next slide, please. We have a huge product line. We do not recommend everything for ceramics. Here is just a selection of the most, let's say, most famous materials. Here we are presenting 3 METHOCEL classes: the METHOCEL A, the pure MC, and METHOCEL F and K classes, all having different viscosities, starting from 4,000 up to 75,000 and even higher. everything is possible, but not everything is always reasonable. So there are many reasons to use this or that formulation, and this is of course subjected to an individual discussion. Also, I should mention we have still some special grades for special purposes and special requirements. We can discuss this on demand. And it's worth to mention, we have also premium grades because we are a big supplier in the pharmaceutical industry. Premium grades contain significantly reduced sodium chloride content. This might be interesting if you want to extrude catalysts. Next slide, please. Yeah, here still mentions the Polyox grade WSR301. This is polyethylene oxide with a molecular weight of 4 million. This is our multi-purpose grade, if you like, as additional lubricant. Yeah, we are open for a discussion. If you like, we can do this offline. You have the address of ChemPoint. We have some customized grades, and I'm happy to receive your feedback. And with this, I would like to finish and open the question and answer session.
All right, thank you, Roland. Let me check and see questions we have here. So we have a couple coming in. 1 second here. Again, if you have a hard time finding the question and answer live Q&A box, if it's in the top right of your window there, a chat bubble with a question mark in the middle. So if you'd like to submit a question, feel free to do so now. All right, looks like we have one question here, Roland. How do the different METHOCEL classes A, E, F, K, and J differ in regards of their content of substituents?
Yeah, thank you. I remember there was one slide in the slide deck showing these boxes. These boxes represent the specification windows, the specification window of each product class. However, the scales, the X and the Y axis, are given in percent. These percents are coming historically from the definition in the pharmaceutical industry, so they are part of the pharmacopoeias of United States, of Europe and Japan and many other countries. And there is still, I should mention, there is still a scientific definition which is different. They are not calculating the methylation and hydroxypropylation degree in percent by weight, but in numbers. So for instance, they consider every glucose unit has 3 hydroxyl groups. So in maximum you can replace 3. So this is a so-called DS, the substitution degree or the methylation degree. You can never add more than 3 methyl groups to the hydroxyl groups. So the maximum is 3. In the case of hydroxypropylation, it is a little bit different because the reaction with propylene oxide can lead to small side chains. So one propylene oxide molecule can react several times, so with each other, no, not with itself, but with other molecules, leading to 2, 3, 4, 5, or 6, or even more smaller hydroxypropyl groups, and they lead to a little chain. So theoretically, the substitution of the hydroxypropyl groups could be much higher than 3, but of course this is a question how to steer the reaction, how much reactants we enter into the reactor, and we have a lot of control, of course, on the reaction chemistry, so we can clearly stay in these windows as we defined them, and they are also mentioned in the specification. And if you receive the analytical certificate, then you know where exactly your batch is located in this box.
Great, thank you. Question here from Amir. Is hydrating the HPMC prior to mixing with other powders an option, or should it be dry mixed with other powders followed by addition of water?
The most efficient way is to start with a dry mix. Dry mix between the ceramic ingredients and the cellulose ether, because once you have water in the system, you get a high viscous material and a stiffy material, and to add another ingredient into a stiff material is much more complex than to make a homogeneous powder mix. By the way, once you have this homogeneous powder mix, you should not pump the water into the mix, because then you will never get an even distribution of water into your ceramic mass. You will always have an uneven distribution of water. We have made measurements, and the distribution differences can be more than 1%. And 1% more volume or less volume is already a reason for crack formation when you dry or when you sinter. So this is very important, not to pump, but to spray the water into the batch. And it is easily done. Yeah, a spray nozzle costs you $10, maybe 20. But this is really not an issue. But you need to guarantee that the water is homogeneously distributed over the whole batch. Everything else leads to very complex processing or 10 hours of kneading time, and this is a nightmare. It's reducing your capacity in the plant, and it is leading to lots of abrasion, costs you high energy, and produces potentially also off-spec.
Thanks. Next question here is, how does shape retention correlate with the different chemistries?
Yeah, very interesting. So this is obviously a question from somebody making a hollow profile, as this is my assumption. I can give you a rule of thumb. To give very nice and good and stable shape retentions, I would my first choice would be always a METHOCEL K chemistry. If you do not have a wonderful control of temperature. If you have a very good control of temperature in your plant, you can also choose METHOCEL A. This works, but you remember the slides and you will receive them definitely. METHOCEL A has a very small window of safe operation, so you must have a very nice temperature control on plant on the plant scale. It's worth to mention that the paste which you get with the METHOCEL K behaves a little bit different from a paste you get with a METHOCEL F. So for instance, the paste ductility with the METHOCEL K type is it is stiffer, and if you bend the profile in your hands, you will see easily a crack formation. So the sensitivity to it's more a rigid profile, where the profile with METHOCEL F is more flexible. Yeah, you can bend it a little bit more before you can see the first crack. This is, of course, a very qualitative test, but you can easily make it even on a lab scale and check the profiles. You can also develop a qualitative test to check the shape retention if you make a 3-point bending test. If you like, we can discuss details offline. We have developed a method which we routinely use. It's a very simple test, a 3-point bending test with a fresh extruded profile, and this gives the first indication in the direction where to go. But you should do it with a full profile, never with a hollow profile, because hollow profiles are drying so fast, they are losing water during the measurement, and you get a permanent deviation of the measurement during the test run. So you need necessarily a full profile just to see the differences in the shape retention data in the different recipes.
Great, thank you. So we have another question here. Can I use the combination of A and K types? And then in addition, is there any plasticity data of paste made with type A and type K?
Yes, combinations are possible. This is not unusual, and I would not expect a major issue. Of course, the gelation temperature of a combination of A and K will not be somewhere in the middle between the two extremes, but the A molecules will gelate there where the A chemistry gelates, and the K molecules will gelate where the K molecules gelate. So this means the total mix will require also a very good temperature control. Then it is possible.
Just see if we have any new questions coming in here. Looks like one other question here. She said earlier, the METHOCEL acts as a binder and thickener. Do you have grades available where there's only binding or only thickening properties?
This is a very nice question. Maybe I said earlier, the METHOCEL is a multi-purpose additive. So you have many properties unified in one product. Now the question leads me to the conclusion, maybe somebody needs something which is just a binder or just a thickener. This is not possible, but you have another option. You can, let's say, we have grades available where the thickening effect is more dominating, and other grades where the binding effect is more dominating. Obviously, is that high viscous materials show a very strong thickening effect, whereas the low viscous materials do not show a significant thickening effect, only a little thickening effect, but you cannot reduce the thickening effect down to 0. In both cases, they show a binding effect. So you can, let's say, modify the relation between binding and thickening. But you cannot reduce the thickening effect to 0 and also not the binding effect down to 0. If you make, let's say, if you formulate a batch, one batch with very high viscous cellulose ether and the same batch with the same amount of a low viscous cellulose ether, you have strictly reduced your paste viscosity. But you have still the same binding properties. Binding comes just from the cellulose ether molecules surrounding the ceramic particles. This remains the same, just the viscosity at the end is different. But it's worth to mention that it might be possible to make formulations with very low viscous cellulose ethers where you have a much more Newtonian rheology, because these you do not have so many long chain molecules, but very short chains. If you do not add a higher concentration of cellulose ether, the Newtonian properties are dominating. This is a very different extrusion process, very stable. But you should please consider that also the water retention capability is a function of the viscosity. And once you reduce the viscosity in a too high extent, then you might lose too much water retention. And this is worth to test. Somewhere there will be a limit. So like always, there is an optimum somewhere and you must find it. But you can try. But definitely I would not choose a very, very low viscous cellulose ether. You know, our METHOCEL product portfolio ranges over 5 magnitudes in viscosity. The lowest viscosities which are regularly sold is, for instance, METHOCEL K3, 3 millipascal seconds in 2%, and the upper end is somewhere in the range of 100,000. There is one grade with 250,000. So these are 5 magnitudes, and of course the properties from one end to the other are changing significantly, but it's possible to do this. Yes, and it might have some benefits in special recipes, but please make first checks that your machinery will not get defects because of the water retention, which decreases too much.
Great. Looks like we have time for one last question here. Is there a general correlation between extrusion speed and pressure when extruding pastes containing METHOCEL?
Yes, as higher the pressure, as higher the speed can be, but not in all cases must be. It is a question of the rheology. And I remember we have made trials 12 years ago with special rheologies of the paste where we could show that we could increase the resulting extrusion speed, so the speed in meters per second coming out of the machine, we could increase the extrusion speed by 250% and at the same time reducing the extrusion pressure. This was a very significant effect and has rheological reasons. There are some tricks behind, and the background knowledge you should have. I couldn't present this because then I had to add 50 more slides. The background effect is the drop of very high, the strong drop in viscosity of very high viscous materials under extremely high shear. They are dropping more than normal viscous materials, and if you run an extrusion process with a complex die and you use, for instance, K100M or K250M in a very low concentration, you get an extremely shear thinning process and you can extrude with very high speeds. We made a comparison test with F4M, which is, let's say, the blockbuster everywhere, and a standard which we are selling in all continents to many customers. And the difference was 250% resulting speed at a lower pressure. So it's not always necessary to have double pressure if you want to extrude faster. This is a real cost saving. Lower pressure means lower energy costs. Yeah, but we can discuss offline if you like. I have some slides prepared. I presented them in a conference some years ago, and this is with a rheological trick you can achieve a lot.
Great, thank you, Roland. It looks like that's all we have for questions. Once again, I want to thank everyone for attending today. Thank you, Roland. Thank you, Lindsay, for presenting. If you'd like more information about METHOCEL or any other IFF products, you can visit chempoint.com. All the information is listed on our website, and you can also reach out to us for more information or samples or quotes via our website as well. So again, chempoint.com for any additional product information and to contact us. With that, we'll wrap this up. Thank you, everybody.
Thank you.